So let us see how the graph of potential energy and kinetic energy versus time can be visualized. We know that the formula for kinetic energy is half m omega square a square cos square omega t, and for potential energy is half m omega square a square sin square omega t. The one thing you will observe here is that there is a square term of cosine and sine, which means that no matter whatever be the value of omega t or cos omega t, the cos square omega t will always be positive. Cos omega t may be positive or negative, but the squaring of that will always become positive. Same thing is for potential energy. So the potential energy and kinetic energy do not turn negative in any part of the SHM cycle. They are always positive. Now having said that, let us examine the potential energy P. We take in the x-axis time and in the y-axis the measure of potential energy. So at t is equal to 0, that means the body is at origin 0, there is no extension. So therefore the elastic potential energy is expected to be 0. Can it be derived from our formula? Yes. At t is equal to 0, omega t is 0, sin omega t is 0. So half m omega square a square sin square omega t turns out to be 0, because 0 multiplied by anything is 0. So we get a point here at t is equal to 0 for potential energy. What about at t by 4? What is t by 4? The t by 4 is the 1/4 of the journey, 1/4 of the total time period, or 1/4 of the cycle of SHM. So in that 1/4 cycle, the body has reached from O to P with maximum extension. And here the potential energy is maximum because there is no velocity here, the kinetic energy is 0, so it is maximum here. So at t is equal to t by 4, or 1/4 of the journey, we expect the potential energy to be maximum. Does it tell it in this formula? Look at t by 4. What is t by 4? The total time period is 2 pi by omega, so 1/4 of omega is pi by 2 omega. We could have divided the time axis as t by 4, t by 2, 3t by 4t, or pi by 2 omega, then pi by omega, then 3 pi by 2 omega, and 2 pi omega. They are all the same thing. So if you find here pi by 2 omega, you put here, you get how much? Sin square omega t at t is equal to pi by 2 omega is sin square omega into pi by 2 omega is equal to sin square pi by 2, this is equal to 1. So it is the maximum value. Sin square omega t is at its maximum, so the potential energy at t by 4 is half m omega square a square. So we can turn this as, this point is half m omega square a square. Now what about t by 2? The body goes here t by 4, comes back here to t by 2, half cycle, it has reached here but it's going toward the left. So at this point here it is again 0. So here it is again 0. Similarly at 3t by 4, you will find out that this, you put t is equal to 3 pi by 2 omega, you will get again a maximum. So here it is again the maximum, here at this point. And when it completes the full cycle, that is, it goes here, comes here, then goes here, then comes here, again the potential energy is 0 because there is no extension. We had, our starting position was this, the equilibrium position, so here it is 0. So you plot you connect these things, you will get, I think this. The peaks corresponds to half m omega square a square. Now, what about the kinetic energy? If we plot the kinetic energy here, what do we get? At t is equal to 0, here the body is either rushing past toward the left or shooting past toward the right with the maximum velocity. So at t is equal to 0, you will find that the kinetic energy is maximum. So you will find that if this is the curve of potential energy, let's plot another curve of kinetic energy. Let us get a blue pencil, a red. for that example. So here is our kinetic energy. At T by 4, you put here T by 4, that is pi by 2 omega, you find that T by 4 is here, at T is equal to 0, T by 4 is here, that means here the velocity is 0, so here it is the kinetic energy. Now T by 2, which means it has gone here T by 4 and returned back here T by 2, so it is shooting past towards the left with the maximum velocity. So here again we get another point for Ke, and similarly at 3T by 4, which means T by 4, T by 2, 3T by 4 other extreme position where velocity is 0, so we get here a minimum kinetic energy and again here a maximum kinetic energy. It's not working. We connect these dots. We connect this. All these positions corresponds to half m omega square k square. So I can lay down a straight line. This is half m omega square a square. This is how it varies, and you can see that wherever potential energy maximum, kinetic energy minimum, wherever kinetic energy minimum, potential energy maximum. Now, after seeing this graph of half m omega square a square is the limit at which it varies, what do you think about the exchange of kinetic energy with that of potential energy as time passes? Please see these points. At this point, the potential energy and kinetic energy are same. At this point, potential energy, kinetic energy are same. At this point, it's same. At this point, it is same. We will calculate later where and in which position the potential and kinetic energies are expected to be the same. Now, this is one of the way to make a graphical interpretation of the exchange of kinetic energy and the elastic potential energy of the body during a full cycle of SHM. Next, we will draw and try to find out what is the graphical representation of this kinetic and potential energy in terms of position of the body.